Hello everyone, welcome to the another session of digital signal processing. In this session, we are going to design FIR filters. So we are going to cover windowing and rectangular window and all other commonly used windows, mainly Hamming, Hanning, Bartlett and Blackman window. So in the last session, we had seen that when we were designing our IAR filter, the response that we were getting was infinite, and we were designing that filter in analog domain and converting them into the digital domain. But when we started talking about FIR filter, where response has to be finite, we have certain digital techniques in which we can design this FIR filter directly. So whatever response we get after the Fourier transformation of a signal in frequency domain, we see that response is of infinite duration, and by using certain truncation techniques, we have to convert that infinite response into finite response. So infinite impulse response is converted into finite impulse response by truncating the infinite series at certain level, say n is equal to plus minus m. So m can be any integer number where we want to truncate that sequence. It will range from any small number, say 7, to any largest number, say 40, or any other sample value which would be suffice for that particular application. So, but this abrupt truncation of the series at certain sample value would result into certain undesired things, undesired oscillations into the passband, which are going to produce certain kind of ringing effect that we had discussed in the last session as Gibbs phenomenon. So that phenomenon is completely undesirable, because whenever we play back the signal in analog domain, we get certain kind of ringing effect, or we can have some abrupt undesired sounds in my signal called bias. So what we have to do? So this is happening because of the slow convergence of the Fourier series near the points of the discontinuity. So these discontinuities are responsible for everything which is called as oscillations, or you may call as the ringing effect appearing into that signal. So it would be completely depending upon how we are truncating a signal. That would give me more oscillations or less oscillations. So these undesirable oscillations, these can be reduced by using a set of time limited weighing functions, which are denoted by Wn, and we refer these Wn as window functions. So they modify the Fourier coefficient in such a way that abrupt truncation is not there, and when abrupt truncation is not there, oscillations or ringing effect would also not be present. So what do we see here? This is certain any anonymous signal. We have taken up the response of that particular signal, and we have taken certain window again in the frequency domain whose response is finite. This signal is tending from minus infinity to plus infinity, and this response, this is ranging from some finite value minus m to plus m. The output response that I get here is truncated response having certain amount of ripples in the passband. So this truncation is nothing but mathematically I would say I'm multiplying these two responses and I'm getting the output. So if I multiply this infinite sequence or signal with a finite signal or sequence, the output is going to be finite. So windowing is nothing but a simple mathematical operation that is called as multiplication. So this is the appearance in the analog domain. Similar appearance can be seen in the discrete values as well. So we may have infinite number of discrete values here. Here I have taken some finite samples and multiplied 2. So wherever we do not have samples, that means we have 0, and multiplication of any value with 0 would result into 0 itself. So if I have here samples, say minus n to n, say I take a integer value minus 5 to 5, so output sample would also range from minus 5 to plus 5. So this operation, I need to remember that this windowing that I am performing mathematically is the multiplication of two signals, one signal being infinite, another signal being finite, and resultant signal is again finite. So where we have to see what different kind of such responses can be generated so that I get as smooth as possible output after truncation. The effect of windowing, the process called windowing, is that the discontinuities in the response that we have shown in the previous slide, they are converted into transition bands between the value on either side of the discontinuity. So this is a point of discontinuity here. This is another point of discontinue here, and we would get certain kind of oscillations near these discontinuities. The width of this transition band, this depend upon the width of the main lobe of this window function W. This is my main lobe of the window function. So how broad this main lobe is going to affect this transition band in the obtained signal. The secondary effect of this windowing is that ripples from the side bands of this W function, they produce approximate errors for all W. So whenever we are designing using this finite truncation method, I'm certainly going to introduce error into my signal. Now this is the quality of the truncation that I need to minimize these errors, but I cannot completely eliminate these errors to 0. So what we have to keep in mind during this truncation, that whenever we are talking about this Fourier transform of the window function, it should have small width of the main lobe. So the way we were showing that this is a central lobe of the frequency response, it should be narrow. If it is narrow, then transition band won't get oscillations at the discontinuities. Second, again, because of this Fourier transform that we are taking for this window function, it should have side lobes that decreases in the energy rapidly. The speed at which the side lobes are decreasing, it should get to decay 0 very quickly. That means the stop band should have minimum number of sample here. So we have to choose, or we have to design such kind of window functions which satisfy these two properties. First property being that the width of this main lobe should be narrow, and the side lobes that we are getting, the energy in the stop band, that should be minimum, or these oscillations in the stop band, they should decay very fast and approach to 0 in few number of samples. So based on these criteria, we'll see different kind of window function that we use for designing the FIR filters. The simplest one is my rectangular window, and we see that we rarely use it because if I'm multiplying any signal with this kind of window function, I know here I have abrupt change. And whenever there is abrupt change, I'm going to suffer from Gibbs phenomena. Just for the reference, we'll see this, that this is one of the window that we never use. So here we see that rectangular window mathematically is being defined as having value 1 in certain range, that is minus m minus 1 by 2 to m minus 1 by 2. At all other values, it is 0. So I'm simply trying to plot its frequency response and see that what kind of response I get from it. So I'll take the Fourier transform of this particular sequence, would summate this sequence, and would see that the function I get appears like a sinc function, where these are stop band oscillations which ranging till infinity. But we are interested in the main lobe whose width ranges from minus 2 pi by m to 2 pi by m. So this is the phase response, this is the magnitude response for this particular window function. Next window is my Hamming window. So in all these windows that we are going to discuss, I need to see that it should not have abrupt kind of transitions from passband to stopband. Some way I would try to make the tapering characteristics. That means this transition from the passband to stopband is slow. It is taking some time to decay down to 0. So more the slope of this curve is, less would be the oscillations or ringing effect. But yes, the larger the transition band, the more energy is getting to be wasted in the side lobe, or I can say the more energy would be present in the stop band. Again, it is not desired. So we would have to make certain compromise between and choose between these two stages. I should not prefer this complete abrupt transition, and I should have a control over how these tapering characteristics or how long these tapering can go towards my stop band. So first function which has this tapering kind of characteristics is a Hamming window, and mathematically it is defined as a function WHN, which is a mathematical formula with certain values 0.54 and 0.46. These are experimentally tested values. At these values, I get a good tapering characteristic where I have less distortion. And I'll see that most of these window functions have this main function is my cosine function. So if I try to draw my cosine function, it appears like this. So this part has a tapering characteristic. So I'm going to use cosine as my window function in most of the windows, scaled by some constant values. These values may be changed to have different tapering characteristic. So these windows are defined in two domains, one for the causal system, another for the non-causal system. The difference is there only of the sign, a negative sign for a causal window, a positive sign for a non-causal window. Similar window which is almost similar to Hamming is the Hanning window, and here again we see the main function is my cosine function, but the coefficient which have been scaled here are 0.5 and 0.5. So again the slope of that curve, cosine curve, would be changed with these different scaling values. Similarly, we are defining a causal Hanning window and we are defining a non-causal Hamming window. So depending upon the application or the system we are designing, we can choose any of these two functions. The third window is my Blackman window. Here I would see again we have taken two cosine functions. Here the first cosine is 2 pi n over m minus 1. Second cosine is a function of 4 pi n by m minus 1. And both of the cosine function have a different weighing factor, that is 0.08 and 0.5, and this has been subtracted from the entire function. So more or less the appearance would be this characteristic only, but their slope would be changed. It has a causal function, it has a non-causal function. Another window is my Bartlett window. Now this is something different from my Hamming and Hanning or Blackman window. You'll see here I'm not using any cosine function. When I talk about 1 plus n, that means I have a certain window which is rising and falling. This is certain value 1. You increase the number of the sample, you decrease the number of the sample, and I get certain kind of response. So this has a quick slope. The decrease is very fast as compared to the cosine function. So for the values ranging from certain interval to 1, it is 1 plus n rising, and it is 1 minus n, that is following kind of characteristic. So this is a different window. I may also call it as triangular window. which can be used for generating some finite response. So when we compare all these windows, I would compare on the basis of the main lobe, because I want a main lobe should be narrow to avoid the Gibbs phenomenon. I should have minimum stop band attenuation value, and peak of the first side lobe should also be minimum. So what do I see with different windows, rectangular, Bartlett, Hamming and Blackman? I get different values of the width of the main lobe. Increasing 4 pi by m is for rectangular window, 8 pi by m is offered for Bartlett, Hamming and I get the widest main lobe for the Blackman window. The second parameter is also arranged in the form of increasing value. The minimum stop band attenuation is minimum in the rectangular window and maximum in the Blackman window. Similarly, if we talk about the peak of the first side lobe, this is maximum in the case of the Blackman window and minimum in the case of rectangular window. But as I told you, rectangular window is never preferred because of the undesirable oscillation existing in the frequency response. So one by one, we'll see that how do we use all these windows for generating a finite response. So here a low pass filter has to be designed. The specification are: the response is e raised to the power minus j 2 omega. The range is from minus pi by 4 to pi by 4. Elsewhere it is 0. So what I have to do, I need to determine the filter coefficient HDN. If the window function is defined as 1 for 0 to 4, so 5 sample, the value is 1. If the value is 1 for these 5 samples, that means I am simply talking about rectangular window. So I need to determine the frequency response of the given response to design the FIR filter. So the simplest technique is the given function, that is HD of omega. I would convert this into HDN. That means the first step in the designing is taking inverse Fourier transform. So this is going to be the common step in all the designing for different windows and for different response function. So for the given response, I'm going to generate the time domain function by taking inverse Fourier transform. Then I'll be taking different sample values. Once I have generated this HDN for different values of n, I'll calculate HD0, HD1, HD2, HD3 and HD4, whatever number of samples are being desired. So if window has been defined for 0 to 4, so that many samples have to be calculated. So HDN samples would be calculated. Now what I have to do, I have to multiply this HDN with window function, which is rectangular here. All the samples of this response would be multiplied by the corresponding samples of window function. So whatever is the length of the filter, we'll perform this multiplication till that particular stage and generate new value of HN. This is 0, this is 1. This new value is my finite response in the time domain. So once I have calculated HD 0, 1, 2, 3, 4, I would multiply it with the window function, because in this numerical window function is rectangular. That means I need to multiply all the samples with 1. That means all the value would remain same. So once I have calculated this H dash n, I need to show its frequency response. So to get the frequency response from time domain to frequency domain, what would I have to do? I have to take the Fourier transform. So whatever samples value of Hn has been calculated would be substituted, the equation would be expanded, and then using some mathematical representation, a concise answer would be obtained. So this H omega, which I have obtained after performing all these steps, is the finite response corresponding to this infinite response. So I have converted infinite response into the finite response by simply multiplying that response with the rectangular window function. Another similar kind of numerical in which I am having this response, which is e raised to the power minus j 3 omega, the range minus pi by 4 to pi by 4. I need to use the Hamming window now. And the length of the filter is 7. If the length of the filter is 7, the sample values would range from 0 to m minus 1. That means the sample value I need to calculate is from 0 to 6. So my first step is this h omega has to be converted into hn by taking inverse Fourier transform. This function has been created. The value of this inverse function would be calculated at different values of n and 0, 1, 2 till 6. All these values have been calculated here. Then I need to talk about the function, Hamming window function. So Hamming window function is defined by this equation. Here I can see the only variable is this n. So I'll put the value of n from 0 to 6 and calculate W0, W1, 2, 3, 4, 5 and 6. Once I have calculated samples for window function, I have calculated samples for the given function, I simply multiply these samples to generate finite response. So these, after multiplication, I get the new response values or new samples after truncation. Once I get the new samples, I need to show the finite response. I'll take the Fourier transform. And wherever we are talking about discrete values only. So it would be discrete Fourier transform. So expanding it, you may show it into the value of e raised to the power x, or if I am talking about digital system, I may represent it in the form of the Z inverse as well. Third kind of numerical, a low pass filter have the frequency response given by this equation. Find the filter coefficient HDN. I have to do nothing. I have to take inverse discrete Fourier transform, and I need to determine tau, the delay factor. How to calculate this delay factor? I am given a condition that this response is equal to this response in which I have negated the samples. So first I need to calculate direct response Hn. In this response, I'll replace all the values of n with minus n. Another response would be calculated. Both the equation would be compared, and from there I can calculate the value of tau. So this is first inverse Fourier transform has been taken. This is the function Hn. Let me calculate h of minus n. This is the another function. Sine being an odd function, it would come out here, cancel out. When I equate these two equations, what is the condition? That n minus tau becomes equal to n plus tau. That means if I say 2 minus tau is equal to 2 plus tau, when this condition can be fulfilled? Only when the value of this tau is 0, then only I can equate these two values. So the same condition is applicable here. So the value of tau for which this condition is satisfied is 0. Similarly, another kind of discussion can be, I need to design an FIR filter where specifications have now been given in a different way. The cutoff frequency is given 850 Hz. The sampling frequency is given 5000 Hz. The length of the response or length of the filter is given to be the 5. And I need to use the rectangular window. So from this given equation, I need to create a standard representation, that is this. So because cutoff frequency is 850, Less than that, the response is 1. Beyond that, the response is 0. Because the sampling frequency is also given, I need to scale down the given frequency. 850 would be normalized by dividing it with the sampling frequency. Now this frequency is given in hertz. I'm talking about omega. So I need to multiply it with 2 pi. So 2 pi into 850 by 5000. So this is my normalized frequency with which I'm going to design my FIR system. So again, the step remains same. I'll take inverse Fourier transform. I'll multiply the response with the window function. Here window function is rectangular, so multiplied with 1. And the newer window function which I am obtaining here, I'll perform discrete Fourier transform over it, maybe representing as exponential power, or I may represent it as Z plane. It's completely my choice of representation. So multiplication of the window function and then taking the Fourier transform to represent the response for given FIR system. So these were different techniques by which we can design a finite impulse response filter. We have another technique for designing these filter, which is based upon the empirical formulas, and we'll see that we get a more practical form of representation using that window. The window is called as the Kaiser window. So we'll see how we work with the Kaiser window to design an FIR response, finite impulse response filter, in the next session. That's all for this session. Thank you.